module, you will learn about the kinematics of rotational motion about a fixed axis. Using the analogy between translational motion and rotational motion, we can better understand the rotational motion of a rigid body. In the kinematics of translational motion, we studied about linear motion. That is, the motion of a body along a straight line path. The rotational analogy to linear motion along a straight line is rotation about a fixed axis. Let us compare these two motions. Corresponding to linear displacement in translational motion, we have angular displacement in rotational motion. Consider a rigid body rotating about a fixed z-axis and let P be a particle in it. When the rigid body is in rotational motion, the particle P moves along a circular path. Since the rotation is about a fixed axis, the circular path of P lies in a plane perpendicular to the axis of rotation. The angular displacement of the particle in the plane of the circle it moves in is equal to the angular displacement of the rigid body. The rate of angular displacement is angular velocity, omega. Omega is equal to d theta by dt. Omega in rotational motion plays the same role as linear velocity, v, in translational motion. Since the axis of rotation is fixed, the direction of angular velocity is always along the axis of rotation, and hence it need not be treated as a vector. The rate of change in angular velocity is defined as angular acceleration alpha. Alpha is equal to d omega by dt, which also acts along the axis of rotation. Angular acceleration is the rotational analogy of linear acceleration of translational motion. In kinematics of translational motion, we studied about the kinematic equations for a body in linear motion with uniform acceleration. For a body moving with uniform acceleration a, the equations are v is equal to v naught plus at, x is equal to x naught plus v naught t plus half at square, and v square is equal to v naught square plus 2a into x minus x naught, where x naught and v naught are the initial displacement and initial velocity respectively. X and v are the final displacement and final velocity after a time interval of t. Now, let us try to get similar relationships in rotational motion. We shall restrict our discussion to a rigid body rotating with constant angular acceleration about a fixed axis. Consider a rigid body rotating about the z-axis with a constant angular acceleration alpha. Let its angular velocity be changed from omega naught to omega in t seconds. We know that the angular acceleration alpha is equal to d omega by dt. Let this be equation 1. On integrating equation 1, we have integral d omega is equal to integral alpha dt. Since alpha is constant, equation 1 leads to omega is equal to alpha t plus c, where c is the constant of integration. Let this be equation 2. But the initial angular velocity of the body is omega naught. That means, at time t is equal to 0, we have omega equal to omega naught. On substituting these values in equation 2, we get c equal to omega naught. Therefore, equation 2 can be written as omega is equal to omega naught plus alpha t. Let this be equation 3. But we know that omega is equal to d theta by dt. On integrating this equation, we get integral omega dt is equal to integral d theta. If the angular displacement of the body is changed from theta naught to theta in t seconds, integral omega dt from 0 to t is equal to integral d theta from theta naught to theta. Substituting the omega value from equation 3, on further simplification, we get omega naught t plus half alpha t square is equal to theta minus theta naught. Keeping theta on the left, we get theta is equal to theta naught plus omega naught t plus half alpha t square. Let this be equation 4. We know that omega is equal to d theta by dt. D theta by dt can also be written as d theta by d omega into d omega by dt. Therefore, omega is equal to d theta by d omega into d omega by dt. Which is equal to alpha into d theta by d omega. Integrating the expression, we get integral omega d omega is equal to integral alpha d theta, which is equal to alpha into integral d theta. Why the angular displacement is changed from theta naught to theta? The angular velocity changed from omega naught to omega. If we integrate the above equation under these limits, we get integral of omega d omega from omega naught to omega is equal to alpha into integral of d theta from theta naught to theta, which is omega square by 2 minus omega naught square by 2 equal to alpha into theta minus theta naught. On further simplification, we have omega square is equal to omega naught square plus 2 alpha into theta minus theta naught. Let this be equation 5. Equations 3. Omega is equal to omega naught plus alpha t. 4. Theta is equal to theta naught plus omega naught t plus half alpha t square. And 5. Omega square is equal to omega naught square plus 2 alpha into theta minus theta naught are the kinematic equations for rotational motion with uniform angular acceleration. Example: a flywheel starts from rest and accelerates with a constant angular acceleration of 0.6 radian per second square. Find the magnitude of the angular velocity after turning through an angle of 45 degrees and the time required. Given that initial angular velocity omega naught is equal to 0, angular acceleration alpha is equal to 0.6 radian per second square, angular displacement theta minus theta naught is equal to 45 degrees, which is equal to pi by 4 radians. We know that omega square is equal to omega naught square plus 2 alpha into theta minus theta naught, which is equal to 0 plus 2 into 0.6 into pi by 4, equal to 0.94. Thus, omega is equal to 0.97 radian per second. We also know that theta is equal to theta naught plus omega naught t plus half alpha t square, which is equal to theta minus theta naught equal to omega naught t plus half alpha t square. So, pi by 4 is equal to 0 into t plus half into 0.6 t square. Hence, t square is equal to 2.62 and t is equal to 1.62 seconds. You have now reached the end of this module. In this module, you learnt that the rotational analogy to linear motion of translational motion is rotation of a rigid body about a fixed axis. Corresponding to linear displacement in translational motion, we have angular displacement in rotational motion. Angular velocity omega in rotational motion plays the same role as linear velocity v in translational motion. Since the axis of rotation is fixed, the direction of angular velocity is always along the axis of rotation, and hence it need not be treated as a vector. Angular acceleration is the rotational analogy of linear acceleration of translational motion. The following are the kinematic equations for rotational motion with uniform angular acceleration. Omega is equal to omega naught plus alpha t. Theta is equal to theta naught plus omega naught t plus half alpha t square. Omega square is equal to omega naught square plus 2 alpha into theta minus theta naught.